And when I proposed the idea that to have a round table of very eminent people, it was strongly supported. And so instead of one visionary giving a speech, we will have for you 3 visionaries, 3 leaders of 3 very great organizations telling you about their vision of what software, where software is heading, and where software engineering is heading, and in particular, what challenges they face. So as researchers, I'm sure all of us are always looking for problems, challenges, what to apply our CPU cycles on, our students put our students on, presumably something that will have an impact. And here we will have 3 eminent people from, as I said, 3 of the largest companies in the world telling us what are the challenges they face. So I'm very honored to have three distinguished people, and I'll just call out their names in the order and then request them to join here. So first, I would request Ananth Krishnan to please come and join. Ananth, let's just give him a round of applause. Ananth has MTech as well as MSc from IIT Delhi, so he's graduated from IIT Delhi and joined TCS straight after college and has been with TCS ever since. I have huge respect for people who build their careers in one organization. Ananth is clearly one of them. Ananth is currently the CTO of TCS and chairs the TCS Corporate Technology Board. He's a member of the TCS Corporate Think Tank and has led several strategic initiatives. He has been a principal architect and lead consultant and head of TCS Systems Management Group earlier. He was named in Computer World's Premier 100 IT Leaders for 2001 and InfoWorld's top 25 CTOs in the same year. He was named a distinguished alumnus of IIT Delhi as well. So he is an invitee on TCS board, and he sits on various boards of various companies and is a senior member of IEEE. So let's welcome Ananth again. I would like to now invite Jeannette Wing. Jeannette is the corporate vice president of Microsoft Research. She's on leave from CMU, where she's the president's professor of computer science and twice served as the head of computer science department. From 2007 to 10, she was the assistant director of computer and information science and engineering at the NSF. She has received her SB and SM degrees in computer science and engineering and PhD degree in computer science, all from MIT. Professor Wing's general research are in the area of trustworthy computing, specification and verification, concurrent and distributed systems, programming languages, and software engineering. She's on the editorial board of 12 journals, including the JACM and Communications of the ACM. She has been a member of many advisory boards. She's currently the vice chair of the DARPA Information Systems, the Information Science and Technology Board, chairs the ACM Infosys Award Committee, and is member of the Microsoft New Faculty Fellowship Selection Scheme. She's a fellow of the American Academy of Arts and Sciences, American Association for the Advancement of Science, the ACM, and the IEEE. Extremely distinguished person we have within us. Please let us welcome Jeannette Wing. And then we have, I would like to invite Vishnu Bhat. Vishnu Bhat heads the Cloud and Mobility and Infrastructure Management Services at Infosys and drives the vision of delivering digital transformation and infrastructure management initiatives for the clients. Vishnu has been with Infosys for 21 years and earlier led the Cloud and Systems Integration Unit at Infosys. Prior to that, he was the COO for Infosys Australia, and where he integrated an acquired subsidiary. He also headed the Global Development Center in Toronto and delivery operations for Infosys in Canada. Vishnu represents Infosys as a steering committee member at the Open Data Center Alliance and has joined the Alliance as on the board of directors. He's a widely recognized leader in the industry for his vision and expertise in delivering transformational impact for the enterprises through digital technologies such as cloud, big data, and mobility. He has been recognized as one of the 101 trust leaders in cloud and hosting 2014 by Total Product Marketing. He has an engineering degree from University of Mysore. So, ladies and gentlemen, we have three distinguished people from very, very large companies, one Microsoft product companies and TCS and Infosys, two largest service companies in India. And if I may add, I have a good association, actually very close association with all three of them, as it turns out. I was a vice president at Infosys for 2 years in my first sabbatical, and I was a visiting researcher for a year and a half in Redmond, and I believe Jeannette's 1-year sabbatical there partially overlapped with my sabbatical at Microsoft. And TCS was actually, as it turns out, the first company when I finished my PhD and started working at University of Maryland. It was the first company I consulted with and actually spent some time with, and I continue to have very good relations with them. So the format of this is that we'll go in the alphabetical order. They've been requested to give a TED-like talk, 20-25 minutes, enunciating their vision and challenges. In particular, I've requested them to state some challenges which may be the takeaways from us. After that, the floor will be open for comments, discussion, and all of the members will be here. Thank you very much. Vishnu, I would like to invite you. Oh, sorry, Ananth, I would like to invite you to start proceedings, please. Can you please?
Thank you. Thanks, Pankaj, for those kind words, and my pleasure to be on the panel. Can everybody hear me? Thank you, Pankaj, and pleasure to be on the panel. And I'm sure Vishnu, Jeannette, and I will enlighten you with what challenges we grapple with, and I look forward to the discussion as well. So let me kick things off with a view on what is it that we as companies which deal with a large number of enterprises globally, of all kinds, banks, insurances on one side, airlines and hotels on the other, and healthcare companies and life sciences companies, manufacturers, all these companies that we as service providers, as consultants, as system integrators, as product vendors, we deal with, give us a certain feedback. And as builders of software, as providers of consulting, as providers of services around software and systems, I've tried to condense that wisdom into about a 15, 20-minute talk. So first, let me set the context of what I think the world of software is going towards. Then I will spend a few minutes on the implications for software and software engineering, and then I would make some suggestions on what future focus areas could be for all of you who work in academia, in industry, in research and development, to debate and discuss in your endeavors to help us become better in this space. So what is the context? The context is, in my view, encompassed by two different aspects of what has happened because of the proliferation of computing over the last 60 or 70 years. From the 1940s, when Watson Sr. is reputed to have famously said that maybe 3 or 4 computers is all that the world would ever need, to today, when just 3 days ago, one of the major Indian newspapers, the Hindustan Times, headlined this Ericsson report saying that the number of mobile phones is going to surpass the human population and cross 7 billion by early 2015. So effectively, the number of computers has proliferated, and there's been a J-curve in that in the last maybe 10 or 15 years. It's not just one order of magnitude, but it's several orders of magnitude of proliferation in terms of number of people who access computing on a personal basis. In fact, if you actually draw the graph, it is astonishing. In the 40s, there were probably less than 100 people who could actually access a computing device and plug wires into the back and work the logic and get results which only they could interpret. In the 50s, it probably went from a few hundred to a few thousand, and into the 80s, it probably went to a few million with the advent of the personal computer, and today it is several billion in some sense. So it is an astonishing audience that we have gathered as an industry, and I think it's never been done before in human history. On the other side, the power of the computing device, even if I just take two intermediate points, the IBM PC and the Windows operating system, the Microsoft DOS operating system in the 80s, and now the Windows Phone as two exemplars. The power of computing has also kept pace with it, and this is, in some ways, the various aspects of Moore's law that have been quoted and talked about. So at one side, the scope of what we do in terms of human consumption has just gone through the roof, and our ability to support it with computing capacity has kind of kept pace with it as well. So that's the first contextual point that I would like to identify. The second is, what is it that people use computing for? In the 40s, in fact, the first computing applications were, no guesses, were for defense applications to compute trajectories of artillery shells and missiles and so on and so forth. And even in the 40s, numerical problems were the big deal to solve. And data processing itself started happening only in the 50s. But today, it has gone from being something which is esoteric and does something which is interesting to maybe scientists or people who might indirectly affect the man on the street or the woman on the street, to the woman on the street and the man on the street. Whether it is the famous Tahrir Square, Twitter-like events in 2011, the Arab Spring, and so on and so forth, to a world today where everybody seems to kind of take computing into their stride. The recent general elections in India were our first E-driven election, with all the major political parties using the electronic media as much as they use physical contact and the conventional media. And this is changing worldwide. So it is affecting people in their day-to-day lives. Right? So the expectation of software is no longer that it computes or it transacts, or it is now part of our lifestyles. Right? So that's, again, a huge contextual point that I'm sure all of us recognize. So what are the implications for us? In people like us who build software, who design methods to build better software and support it through its life cycle and evolve it and adapt it, here are 3 or 4 things that I suggest are important implications for us. The first is scale. What we build is no longer meaningfully measurable in terms of lines of code and so on and so forth. I read this astonishing figure, which I don't know whether it's true or not, that the healthcare.gov system or application or website or whatever you want to call it has got 500 million lines of code in it. I can't believe that kind of a number. It's reputed that Facebook has north of 50 million, 60-something million lines of code. On the other hand, the stuff that really does interesting work on the scientific world is also not small anymore. Right? The Large Hadron Collider has 3.5 million lines of code. Now, these are astonishing numbers. When we were growing up in the first computing, I remember my first computer program in the late 1970s was about 15 lines of Fortran code. Right? And that was about all that we could get our heads around, and that was reasonably good if you made it work. Now we're casually talking about millions of lines of code. We're talking about environments to execute our code are no longer these well-understood von Neumann-like machines. In fact, the earlier machines were, more or less like the block diagrams that we learned as the abstractions, They had well-defined memory, they had processing, they had storage capacities, they had input and output and so on, and we could sort of understand that mental model. Today, for someone to actually understand the distributed environments to which we program into, it's not easy. And in fact, a lot of the new generation of programmers don't really now get it in terms of what is that physical environment that they're programming into. You're just programming into some fabric which has certain behaviors, and you sort of take it for granted and you just go. I mean, there are, my 13-year-old son is now cutting and pasting snippets of code and writing API-based applications, if you will, without really understanding that abstraction which lies underneath that whole story. So that is reality now. People don't really understand the actual models of what is it that underlies the environments that we do. Thirdly, devices, because of the proliferation. Today, software is no longer written for well-understood computing. I had pictures on my previous slides of the ENIAC and the IBM PC and so on, and these were well-understood. This is a computer, and you write code to that computer. Today, you write software which might reside in RFID dust, which is a microscopic compute device which has all the attributes of a computer, so to speak, which are useful for us so that we can actually write to that physical implementation, but it's anything. The Google Glass is there, and the tablets are there, and drones are there, and so on and so forth. So you write software for all kinds of things. So that's another aspect of reality. You don't write software only for computers, you write software for things. And lastly, what I mentioned about 13-year-olds is largely true. Now, DIY, do it yourself, is there. Now, imagine we as a guild, if we were a guild in the 1500s or the 1400s anywhere in the world, of saying we are software smiths, just like goldsmiths or iron makers and so on, our guild is being invaded by people who kind of know what we do, but they want to do it themselves. So people are now writing their own applications. There are accidental developers, people who are actually doing fairly complicated programming by dragging and dropping things on things that we have provided them. And those consequences are way beyond what we might actually have designed those drag and drop interfaces for. So there is a whole new class of whatever I've called accidental developers or accidental software engineers who are now part of our community, whether we like it or not. So these are 4 realities that I thought would be the first set of implications of where we are today and where we are going. What are the consequences of these realities? I think we now have to understand that new paradigms are there, and we have probably created most of them, but these are now a runaway train which is going beyond what we have created. Layers of abstractions is my way of looking at this way of API-based programming, which is now pretty popular. In fact, a lot of the platforms that we are getting used to, whether they are the e-commerce or the commerce platforms, they are the social platforms, whether they are the informational platforms and so on, all of them offer extensibility through these layers of abstraction. So they will all provide APIs. There are API marketplaces. There is ways by which you can mash things up, in which developers can get meaningful code out in a day and find an audience for that and make money on it or provide some social benefits on it. So this layer of abstraction, which we have been actually trying to rigorously develop, is already there and it's beyond us. And this is now an expectation which not just casual programmers have, but even serious developers have. The rate of change, I think, is enormous. The way in which a business expects to find new capability and find it quickly, and then find the software to respond to that business capability, is no longer measured in years or even months. It is now measured in days. So a CEO or a board who wants to get into a new market or to launch new products, whether they're physical products or whether they are intangible products, does not have the patience when an IT department or a CIO comes up and says, this is going to take us 2 years to build. It might actually have taken 2 years to build in the past. But today, you have to be able to deliver that capability in days, weeks at the most, definitely not months, definitely not years. And while agile is seen as something which is still being understood at scale, in many of these kind of leading edge expectations, agile is not good enough. People say, what do you mean you're going to take 90 days to deliver something? Somebody else is going to do it faster than us. The second implication or the consequence is on the real focus on consumability. From the days in the 40s where consumability meant nothing, if you wanted to use a computing device, you better know how to plug wires into the backplane of a computer, to paper tape, to punch cards, to the early days of CRT terminals, to DOS, to Windows, to all the graphical user interfaces that we are now used to. Consumability of the application, consumability of form factors, diversity in user groups, consumption over networks and data that you have no control over, all these are given. So when a social network deploys its software, it has to be able to understand that that software is going to be consumed on all kinds of devices, over all kinds of networks, under all kinds of conditions that nobody has any control on. So how do you now design that consumability and that experience? Scale is going up all over again. People are now talking about applications which will routinely have 50 million, 100 million, 500 million, a billion users. And that's not one or two applications, but all kinds of applications. Any governmental system that we launch in this country, which has impact on citizens' lives, has to have a scale of at least a billion. Otherwise, it's not going to cut it, because that kind of demand exists in the usage of those systems. And lastly, while software systems, maybe because of the first wave of things that we were asked to do in the enterprise world, in the governmental world, and so on, not the scientific world as much, but today all these worlds are converging towards data-centric applications. It's not that we didn't know what data was. In fact, one of our nicknames was data processing. But today, the scale at which we are dealing with data is leading to a new class of applications related to insights, related to prediction, related to intelligence, related to the way in which people would want to use the data, other than just transacting with it. So these are the four consequences: design, consumability, scale, and data itself. So here are my suggestions for what you might like to respond to. And I know that in ICSI, you have had tracks, the future of software engineering, and many others. And it's good to know that forums like this exist where we can sort of sanity check each other on where is it that we are heading from an industry perspective and where the challenges lie from a research perspective. I head research and development for TCS is one of the things, important things that I do for the company. And I try to bridge this across our own organization, our research teams and our engineering and software service teams. In fact, 4 of these examples that I take are things that TCS research is already working on. So if we need to have a conversation on the side, I'd be more than happy to do that. So what are those 4 things? The 4 things are: challenges exist in the way in which we want to look at software and process, the way in which we want to look at models and model-driven development, the way in which we look at assurance, verification, validation, and then the new areas that I talked about. Let's take a brief look at each one of them. I think the fact that software is built by people, even if some new software will be built by other software, I mean, I'm discounting that, but originally, I guess, a lot of software will continue to build by human beings. I think we need to apply a lot of what the systems engineering folks call systems thinking into this. Treat enterprises as complex systems and apply those principles that complex systems understanding and systems thinking folks have done for the last 30 or 40 years, apply those to create better software. I know it's not intuitive. Systems thinking by itself is not an easy science. But I think the time has come for us to try and grapple with the complexity that we need to face up and use these kinds of techniques. Knowledge engineering is another science which has been at the edges of software engineering. But I think we need to now go beyond what we have already done and look at, we have done things around process, we've got maturity models and so on and so forth, and that has allowed us to scale up to a point. But I think we now need to start looking at knowledge itself and codify it, create those domain models, create those experience models, create those tangible and intangible models, the tacit and implicit knowledge that resides in each of us, and try to externalize that so that more and more effective teams, more effective software collaboration can happen across the larger and larger teams which will build software into the future. And finally, non-functional requirements. We are probably not as good as software engineers in understanding what the right-brained aspects of our science are. We're fairly good, I would say, in understanding the engineering aspects of here is the logic, here is a requirement, and here is what I need to do algorithmically. Everything else we sort of conveniently bucket into non-functional requirements, whether it's usability, whether it is scalability, whether it is consumability of the software, as I said, and many other things. I think this has to dramatically change as we go forward. The expectations, as I said, of millions of people, billions of people who use software are very different from somebody who was giving us requirements 20 years ago or 30 years ago. A lot of the non-functional requirements are actually the requirements, not so much the functional requirements. How do you elicitate that? How do you design for this? How do you benchmark it? And then eventually, how do you trace it and improve it? I think that's an area which we need to make it much more respectable than what it has been so far. What about models? We have had a lot of experience in building models for all different phases of our world, whether it is the business requirements, so to speak, the business end users, us as people building systems, developing software, and then colleagues of ours who might be asked to run, manage, and sustain it on IT infrastructure. Each of these classes of people have built their own abstractions, their own models, their own ways of depicting their understanding of their worlds, and there are intersections that are typically filled in by human glue, whether they're called enterprise architects or IT architects or infrastructure architects. These human beings have now made these three different worlds talk to each other. I don't think this is sustainable going forward into the future. First of all, those boundaries are blurring, as I said. It's very difficult for people who are in those clean silos anymore. It's becoming biz plus dev plus ops, and there's an acronym biz dev ops, which I'm sure many of you are already aware of and probably contributing to the state of the knowledge. But I think the key thing to understand is that these three silos, these three different categories and families of formal and informal descriptions have to start working together and eventually probably become one description and allow people to now live up to that scale, that consumability, and all the other attributes that I talked about. Assurance is the third dimension that I'd like to cover, which is about not just saying that I've delivered good quality or I've verified and validated what the quality of code is, and then say that here is what it is, and you can now analyze it and prove mathematically that these are the critical paths, or these are the areas of code which need formal verification, and so on. But you have to be able to drive a mindset to say that this has to be a convergent solution towards zero defect, otherwise it's not good enough. The expectation of correctness hasn't gone away at all. Whether somebody is on a social network platform, whether somebody is driving a car, whether somebody is performing surgery with a software-based system, all these people take the correctness of software for granted. The correctness of software in the lives of millions of people is orders of magnitude more important and more, shall we say, potentially damaging than it was in find the greatest of 5 integers that I wrote in 1978. So that's the challenge. How do we now drive our processes, our tools, our methods, our engineering capabilities towards zero defect? Lastly, two examples of the data-centric applications that I mentioned. One is a classic enterprise information fusion kind of application set. A lot of the systems that we build today will be in that sense, analyze, and exploit kind of paradigm that this chart describes. There will be things that we will ingest, whether they are things being ingested from supply chains or they're being ingested from social networks or sensor networks or public media and so on. There will be lots of analytics, and that bottom box is probably the richest and the fastest growing area for algorithms, for software engineering, for data people, for social scientists, everybody around the planet. There are books being written about it. And I think that's an area that needs to enormously strengthen as we go forward. And then eventually the actuation of the consequence on the right side is again going to be driven by software. So this class of sense, analyze, and exploit is I think, going to be enormously important. And if you're not already building methods, techniques to engineer this across the life cycles, I think it's a good opportunity to do so. And lastly, systems are coming closer to humans and populations. The social network part, which we are all familiar with, is now invading the enterprise. It's invading the academic world. Not just as fun. Social networks were fun. I found this and I shared this and I tweet this and I have pictures and so on. I mean, that's social networking for fun. But now, social networks for work are what we are talking about. It's about making the human condition better because you are able to share knowledge, you're able to connect, you're able to collaborate. Is it possible, for example, to get rid of workflows? Why did we have workflows? Workflows are almost a direct implementation of an industrial age construct, which was the assembly line. In an assembly line, you would do a certain task by dividing it up amongst 10 people and letting that work element flow across one to the other. And eventually, a finished product would emerge. Workflows, in many ways, are similar to that. We just took that concept and implemented it in software. But today, if you have the ability for all the 10 participants in that intellectual process to work together at the same time, work doesn't have to flow. Work can just happen because the 10 of us who need to be together to look at something or take a decision are all there, and we can work on it together and finish it off in probably 1/10 the time with all the benefits of that. So social networks is one human-centric side of applications that need probably a very different way of thinking about software. And then on the other side, the aspects of human populations dealing with human condition, including software development itself, can be now an area of work which can engage all of us. How do you put together the best possible team to work on a project? Today, it is done by experienced people, team leaders, project managers, whatever you want to call them. Is it possible to do this in a way which makes the team most productive? So that's to use aspects of human psychology, team dynamics, past performance, personality, social behavior, whatever, and come up with the ideal team or the suggested ideal team which can probably deliver faster, better, cheaper software, and so on. So there's all kinds of areas where social science can now work with computer science to produce better software. So that's basically what I had to say. I set the context by saying there is a J-curve going on. I talked about certain implications for us in terms of scale, in terms of expectation, in terms of complexity, in terms of new kinds of applications which need to come up. And then I'm leaving you with 4 thoughts of bringing in systems thinking, bringing in formal methods and models, bringing in verification at the next level, and lastly, to build and think about new classes of applications which might change the way we live in this planet. Thank you. I look forward to your questions later.
Thanks, Ananth, for a wonderful talk in very nice 3 succinct sub-themes. May I request you to maybe write down some questions that you may have? I think it will be best if we take them together with all 3 panelist members. May I now request Jeannette, and please can someone pull out, yeah.
Am I on? No. Okay, can you hear me? Can you hear me? So, we were supposed to talk about emerging software engineering challenges, and of course, any challenge is an opportunity, especially a research opportunity. But even if I thought about talking about challenges and opportunities, I thought it would be more important to talk about the roots of those challenges and opportunities. So I titled my talk, Emerging Trends in Software Engineering. And there are a lot of trends, many of the ones that are not already talked about, I'm going to talk about as well. So I thought, just for the sake of some way to categorize our thinking, to be simple about how to present some of these trends, I would talk about it in terms of scale, speed, and security. And so for each of these, what I'm going to do is present a little more detail about what I think are the challenges under scale, speed, and security, and what are some of the opportunities, especially research opportunities, for us to address these challenges. And in the first two, scale and speed, I actually want to give you a couple of examples taken from Microsoft Research as to how our researchers at Microsoft are already addressing some of these challenges. But these examples are really meant to suggest new research directions, especially for the PhD students in the audience. So let me start with scale. There are many dimensions of scale that we can be talking about, and I'll just mention a few. First of all, we're going to be talking about more code and more software artifacts. And each of them lives at different lifespans, very short to very long. So instantaneous temporary file to legacy code. Another dimension of scale has to do with the platforms that our software are going to run on, and the many of them, the diversity and the quantity. So let's start, of course, with the desktop. We are very familiar with the software that we build for desktop platforms, but it's more commonplace today to talk about mobile and cloud. So for mobile, of course, we're talking all the way from phones to tablets to laptops, and of course the cloud at the other end. What two emerging trends I believe we should be on the lookout for is at the very low end, Internet of Things, where we're talking about low cost, very small sensors and actuators. Think about that thermostat in your home, for instance, or a sensor in your refrigerator that will tell you when there's milk to be bought, all the way to larger cyber-physical systems, which would be planes, cars, perhaps robots of the future. These are going to be platforms that new kinds of software are going to have to operate on. And for cyber-physical systems, one of the main challenges there is reasoning about uncertainty, because these platforms and the software that run on them are going to have to deal with the physical environment, with the physical world. And Mother Nature, of course, is unpredictable. Another trend in terms of scale has to do with additional performance requirements that are demanding attention of the software developers when they're writing software on these kinds of platforms. Of course, we care about correctness. This is a tried and true performance requirement that will never go away, and especially for life-critical systems, safety-critical systems, safety and correctness will be of paramount importance. Of course, we care about speed. We always worried about efficiency of the systems that are running. But more importantly, we're going to care about storage and power. So for instance, we worry about the battery lifetime of our phones. We also, at the other extreme, worry about energy-efficient data centers. So power is going to be as important a dimension of performance as correctness and speed. And then, of course, security, usability. I'll speak a little bit more about security. Usability is as very important because of the masses of people who have high expectations of our devices, of our software running on the devices. And finally, another dimension of scale has to do with the people, the processes, and the organizations that are using our software and our systems and our devices, but also producing our software and our systems and our devices. So there's this very new software development ecosystem now where we have tens of thousands of app developers, many of whom do not have a degree in computer science, which was unheard of maybe 10 years ago, where normally if you're going to be a software developer, you work for a company as a software engineer, you probably have had some kind of undergraduate degree, undergraduate training in some kind of computing discipline. Today, anyone can write an app. Anyone can write a website. So it's a very different situation in terms of who the people are in developing these software systems. And that means the kinds of software that they're developing are all part of this bigger ecosystem, sitting side by side software that's developed by professionals. Very different world. Okay, so what are the opportunities given these many dimensions of scale? Well, I'd like to focus on two. One is, not surprisingly, the advent of big data. We can be, in our own field in software engineering, be taking advantage of the more artifacts that we are producing as we're developing software and as we're analyzing software. So I'm going to give you a hint as to one project going on in Microsoft Research. It's been ongoing, actually, in use at Microsoft on data-driven software engineering. Another trend to address scale is to provide tools for software developers that are smarter, that take into consideration the semantics of the program, not just the syntax of the program and the systems. And so I'm going to describe a tool that can be viewed as a tool as a service that is a semantics-based programmer's assistant. So I'll walk through these very quickly. First, there's the data-driven software engineering work coming out of Microsoft called CodeMine. And it starts with the premise that just collect data. And once you have a lot of data, then you can do some interesting analyses on the data. This is a slightly busy slide, but you can see here, basically, we've got lots of source code. Here's the source file. There might be a change made to the source file. The source file includes procedures and methods and classes. A change will induce a branch in the whole source code development, and there might be some integration. And that's just the source code. Then you've got building and testing and information about the process itself, like the schedule. And then you've got, at the front end, you've got people are saying, please add this feature, please fix this defect. All of these elements can be part of a large database. And then, on top of that large database, which let's just say is stored in here, you can build an API such that you can start querying this database and asking questions about fault prediction and what-if scenarios and so on. So this CodeMine repository that I'm showing you here is actually in use at Microsoft by many of the major products Azure and Bing and Windows and Xbox and so on. So any major software enterprise or software company today very likely has such a database of artifacts which can be mined to answer interesting queries. The second example I wanted to show that addresses the issue of scale is to actually create tools that are smarter, and then think about having these smarter tools as actually provided through some service, for instance, through the cloud. So here's an example of a programmer's assistant, a smart programmer's assistant, and this is a snippet of code that's taken from the textbook algorithm of binary search. And you'll see the green squiggly lines here really are suggestive that there might be a problem in this piece of code. And it's the smartness of the programmer's assistant that is suggesting that there might be a problem. And sure enough, it will suggest, for instance, a precondition that you can place in order to protect the caller. And also, more interestingly, it actually knows about the representation of integers, because there are only finite number of integers that can be represented in a real machine, so that it fixes this problem of possible overflow when you're doing the addition. So this tool that I'm showing you here is called Smart Programmer Assistant, and it really relies on being able to walk through the code, create the abstract syntax tree, and then, oops, sorry about that, and then use abstract interpretation over this tree to actually do some semantic inference. And so there's a lot of different kinds of errors that it can detect and suggest corrections to. So that was scale, and those are two examples of some research that's come out of Microsoft that addresses some of these challenges that scale brings us. Let me talk about speed. The challenges here is the first and foremost really new thing, I think, say from 5 or 10 years ago, is the pace at which software is deployed. It's not one of these 18-month, 2-year cycles where you start and then 2 years later the software is spit out. It's one of these daily kinds of events where, in fact, we know it's already difficult to draw a line around spatially the piece of code. But now it's very difficult to draw a line temporally about what that software system is. Because you could put out a new feature, you could put out a patch, whatever you could do, you could put it out immediately. If it's a service, a software service, then it gets out there. And so it's a very different way of thinking about deploying software. And so what that means is the focus is not so much on drawing a line on around your system, either spatially or temporally. The focus now should be on the changes that you make from one instant to the other, or spatially by adding new pieces of code. And so I'm going to speak to some project that focuses on change. And the other thing is that it is about services now. It's not so much about boxed software. And even Microsoft is not just a software company now. It calls itself, we call ourselves a devices and services company. So let me speak about this focus on change. And this is a project going on at Microsoft on change analysis, which I think is very insightful in that it uses state-of-the-art verification techniques that have developed over the decades to take our attention from correctness to relative correctness. And so if you have two programs, P0 and Pn, and you have some kind of one-to-one mapping between the procedures and variables between the two, then in absolute correctness, in the end, you actually want to show for all x, p of x, some property holds. But for relative correctness, you simply want to find an input, say some n, where all assertions will pass for p of 0, and you only need to find some assertion where which fails for p of n. And so you're not doing equivalence checking between p0 and pn necessarily, but what you can do very quickly, and it is more tractable than traditional assertion, is to compare p0 and pn and find that input for which it's correct, if you will, it works for p0, and there's a violation on pn. So this is practical and useful. And this is illustrated in this tool called SIMDiff, which takes two programs, P1 and P2, and it can determine whether there's a difference between the two. And the beauty of this SIMDiff tool is that it's agnostic to any programming language, because P1 and P2 are written in this intermediate language called Boogie, and it uses the Microsoft Z3, Z3 constraint solver. So together, all of this technology that we have been inventing for a couple decades now already has come together to do a very fast relative correctness checker. What you can do then is, of course, feed in, say, 2 pieces of source code using the same compiler, and then you can do a comparison. You can do a diff analysis. Interestingly, you could also feed in the same piece of source code, but to 2 different compilers, and do a diff analysis there to see the difference between your compilers. So there's a lot of possibilities that one can use this kind of SIMDiff tool for. And this is just an example of the kinds of checks that you can do, the kinds of changes, quick changes that people do when they're developing code, that you can use this SIMDiff tool to determine whether a change has been made or not. Another area that I wanted to talk about with respect to speed is as we are deploying pieces of code and software systems in general more rapidly, how do we catch up in terms of validating what it is we're deploying or testing for properties that we care about as we're deploying? So one idea that I'm taking from my colleagues at Microsoft is this notion of targeted testing. And the example I'm going to show is actually a security example, and it comes from the fact that there are many, many products at Microsoft that parse files. So there are many, many file parsers in many of our products, and it's very easy to get your parser wrong, and if you have a security vulnerability in your parser, it costs Microsoft money. So each security patch costs Microsoft alone $1 million. So these are $1 million bugs that might be in any one of these parsers. So wouldn't it be nice if we could test these parsers for these security vulnerabilities? And the typical way that everyone in all software development uses for testing is black box testing, black box fuzz testing, where you have a piece of software, you feed it some input, and you look at the output. The problem with black box testing, of course, is you can't possibly test all values of all input parameters, so what you probably do is randomly choose a few test values, and the problem there is you might miss exactly the test values that will demonstrate the failure. So in this particular case, you'd have to test 2 to the 32 numbers to determine whether there's a failure at all. And then you don't want to do that. So in the approach that we developed at Microsoft called white box fuzz testing, we get to look into the code, and we can then use again, constraint solving, following the conditional flows of the program to generate more wisely, more judiciously, the test cases. And this white box fuzz testing is used at Microsoft, and there actually was an ICSI paper on this a few years ago. This, for instance, since 2008, Sage has been running 24/7 on hundreds of machines, automatically fuzzing hundreds of applications in Microsoft security testing labs. And a telemetry service for Sage has logged over 3.4 billion constraints solved, which is probably the largest, as far as I know, computational usage of SMT solvers. Okay, and I wanted to quote Patrice, a colleague of mine at Microsoft, because it was really his email message to me that mentioned this term targeted testing, which I very much liked. In the world of software as a service, we test less because we have less telemetry and because we update more cheaply and quickly. But we actually need to test more for worst-case scenarios, security, performance, all those other performance demands I mentioned earlier, because damage can be greater and happen more quickly. So the suggestion then is to do targeted testing, for example, looking for specific bugs, for example, looking for security vulnerabilities in specific classes of software like file parsers. Much like 10 or so years ago, again, coming out of Microsoft Research, the SLAM project focused on looking for bugs in device drivers. Okay, so now let me finish up with security, which is, I think, always going to be with us. And the challenges, of course, first, legacy code. It's not going to go away. We will still have legacy code for at least another 10 or 20 years, and that's going to mean we still have to address the legacy code problem. But also, there are going to be new kinds of software systems I alluded to earlier in terms of Internet of Things, cyber-physical systems, and so on. Another challenge is we at Microsoft use a security development process much as along with our software development process. So we build threat models. We look, as we're developing software, for security vulnerabilities. It would be nice if this were the norm for all software companies or for all developers of software. This is hardly the standard, if you will, today. But it would help us increase the assurance of the software that's out there. And of course, as for security, we need to anticipate new threats. And it would be good if we can detect these attacks early and respond effectively. And finally, I think it's not just security. As we are in this world of big data, we're in a world where third parties, government, and who knows who else collects a lot of data about individuals, about our behavior. We also need to worry about privacy. So the opportunities are to build new tools and languages to make legacy code safe. I think there's a new direction for the formal methods community to look very seriously at hybrid system verification. This has been ongoing. I see now much more activity in the programming languages community. For instance, inventing probabilistic programming languages to reason about probabilistic behavior. And there's a talk about that after this session. I think much as the security community has, in the security research community has been in search of a science of security, we have to start doing the same for privacy, looking for a science of privacy. And here it's absolutely necessary to look beyond just computer science. We need to bring in the social scientists, the legal scholars, policymakers, even philosophers who have thought about the meaning of privacy for decades. And finally, in terms of trying to make secure software development processes more normal, more of the norm, I think we still need to educate software developers, educate our students in colleges and universities to be building software with security in mind. So, just to summarize, my trends are scale, speed, and security, and I talked about 2 examples of research projects that address scale, 2 examples of research projects that address speed, and just summarizing some of the challenges and opportunities for security. So this is a great time, actually, to be a PhD student in software engineering because there are tremendous research challenges that remain for you to solve. Thank you.
Thanks, Jeannette. And now our third and final speaker of the panel, please, Vishnu. Do you know where yours is?
Yeah, no, I think it's not. Hold on. Hello? Hello? Yeah, thank you. Thanks, Pankaj, for this wonderful opportunity. This one should work. Is it working? Yep. All right, thanks, Pankaj, for this wonderful opportunity. It's always unnerving talking to a room full of researchers and following speakers like Ananth and Jeannette. So let me give you my perspective on what are the key things that we are looking at from I think we need to get the PPT on, from a software engineering perspective. But I would like to take a perspective that's very enterprise-centric. That's my scope in terms of what does this mean from a next generation enterprise standpoint. I would like to spend a few minutes on the key themes that actually at a high level is something that is profoundly changing. Some of that has been already highlighted by Ananth and Jeannette. I would like to give a 3-pronged approach, or at least a view on this point. First of all, as Jeannette said, there is a theme of scale, there's a theme of speed, there's a theme of security. I think very well said. I would like to bring a very different perspective along with these 3 themes that Ananth and Jeannette spoke about, is that of scope. What is the next generation scope for the enterprise? How do we look at the entire theme of scope in the way we have looked at things in the past? Are there key shifts in our mindsets that we need to inculcate when we build software? Are there key themes that we need to change from a perspective that we have always had in the way we look at the enterprise landscape? Is there key themes that we need to change when we look at 3 key elements as we see the evolution of the enterprise? And I kind of divide this into 3 large buckets of what I call as premises. The first premise is that of compute. We have traditionally always believed that compute was captive. The compute that we all dealt with was secure, was behind a firewall, was contained, was managed, and was hardened. As we see it today, I believe that about 60% of the enterprise IT workloads will reside in the cloud in the next 3 to 4 years. First of all, when we talk about cloud, the first thing that comes to mind is infrastructure. And that's a very wrong notion. Cloud is not just infrastructure. Cloud is infrastructure, cloud is compute, cloud is storage, cloud is applications, cloud is software, cloud is data. If you look at this picture, that 60% of IT workloads will reside in cloud in the next 3 to 4 years. What would that look like? You have an enterprise with legacy assets. It's going to stay, absolutely stay for the next 15, 20 years. There's going to be a construct of data centers as we know it today, but probably highly automated, highly self-service oriented, highly automated. And there's going to be a multi-cloud environment that has significant components of cloud environments associated with it. Infrastructure as a service, platforms, software as a service, business process as a service, and where is this ecosystem leading itself to? Where is your software? Is it in premise? Is it outside? Is it an application residing on an infrastructure as a service backbone? Is it application as a service? Where is the data? What is happening to this ecosystem? I think that is the fundamental shift that we need to understand is undergoing in the enterprise today. What we knew as captive infrastructure, what we knew as captive landscape, what we knew as captive data is just going into a completely different direction of a fragmented ecosystem, and we need to deal with that. I think as you look at this evolution, the first thing that from a scope standpoint that comes to my mind is there is a static nature to our design. Traditionally, when we look at design, there's a static nature to the design. We knew that there was so many boxes in the data center. We knew that there was a certain set of operating systems that we work with. We knew that there was a certain set of data that we had. We knew that we were going to deliver this onto devices of a nature that we always knew. But I think what is happening with this trend is this ecosystem is evolving into a continuously changing setup. New technology is being introduced every quarter. New commercial models are being introduced every quarter. New themes are being leveraged every quarter. So I think as you look at this picture that the enterprise, the world will become extremely hybrid in the next 3 to 4 years, really has to change the scope from what we think as what was static in the past to a highly dynamic, continuously evolving ecosystem, and we need to be ready for that. The second component I want to talk about here is information. We talked about compute, we talked about storage. Let's rethink information. And the first thing I think which is a big change for us again here is the scope. Traditionally, when we looked at software development, when we looked at analytics, when we looked at transaction processing systems and so on and so forth, the scope of information was limited to a large degree. It was limited to structured data. It was limited to data relationships that we understood. We created this whole theme of master data management, master data as a framework for data design. Is that true going forward? Is the scope of data what we have known in the past? If you look at from an enterprise standpoint, the scope of data is just changing. It now includes unstructured data. It now includes information that we never knew was part of the enterprise landscape in the past. And let me give you an example. We were having a conversation with a client of ours. I mean, it's a retail organization. They actually are involved in DVDs and books, and they have stores in different parts of the United States. And very recently, they discovered, and they've been in business for a long time, very recently they discovered that there's a very strong relationship, correlation between the sales in a particular store and declared storm. And we have a lot of these case studies. You must have been hearing about a lot of these things, but I just want to drive home a point. Recently, they discovered that there was a strong correlation between declared storm in a city and sale in a store. So they're in the business of books and DVDs. So it makes common sense. When there's a storm declared by the state or by the city or by the council, People went and bought more books and DVDs, believing that they wouldn't be able to leave home. But the fundamental problem here is that storm data was not part of your master data in the enterprise. Therefore, we completely missed it. Now, if you look at the overarching information that is available for the enterprise today that tells so much about the enterprise, which is residing within the enterprise, which is all we have been focused on in the past. There's information about what the consumers and what the customers are talking about the enterprise, which is filling the social media. We know these case studies a lot. There's a whole host of information which is outside all of that, which has a significant implication to businesses and decision making in the business. But the problem we have is we have been wired to write software based on data relationship that existed and we know existed in the past. And that's the fundamental change when I say rethink scope of information is that theme of known data relationship as being the fulcrum of design and software definition is changing to becoming more about identification of correlations that make sense. Today it applies very much to analytics, and we can relate to this in analytics. However, we believe that this will transcend into transaction processing as well. And one more thing that I think is important to understand here is the dynamism of that data construct. The data construct that is in scope is likely to be so dynamic that we need to be enabling for the dynamic nature of this data to start taking effect in the enterprise landscape. So how do we start looking at defining software? Actually, recently in a conference in Europe, I was actually conducting a session like this with Ken Kukier, who is the economist, the data editor of The Economist, and he's also the author of the book called Big Data. I made a very provocative statement in this. I said, is master data management dead? Is it valid in the way we will look at enterprise data going forward? In the context I was talking about, where the storm data was not part of your master data, what really is your master data? Is it static? And if that fundamental premise changes that your master data may not be static anymore, how do we look at constructing software? And that's a fundamental premise when I say change of scope means a lot to the way we look at software going forward. And the third thing is that when we look at insights, and especially this applies to information management as it applies to analytics, is today's world when the scope of data has changed, the traditional method of, hey, give me your requirements, I will give you software, will be history. Because in the ever-changing theme of shift from data relationships as we know in the past to data correlations which needs to be understood and discovered, requirements are not known. Themes have to be discovered. And I think in that theme of discovery, our paradigm of knowing requirements before you can design software may not necessarily apply. And that is a key shift that we need to start to understand. What does it really mean to build software of the future in the construct where data and information is pervasive, is expanding, and is all in scope, and the nature of which we may not really know when we start defining our software. And that's something that I just want to leave on the table here. The third thing from a data perspective is, for example, 64% of the companies have already invested in big data technologies, but most of them are really struggling to derive value. Because the fundamental framework of leveraging value from this ever-exploding data and bringing that into the scope of what an enterprise needs to look at has still not been addressed, and there's a lot of work to be done in this space. And the third thing I want to highlight here is rethink end-user computing. Again, we have been bottled with what an end user would like to consume from. There is an ever-changing scope of compute as we saw, but there's also an ever-changing theme of the end-user computing itself. What is the device you will deliver your information to? Is it static the way we have seen in the past? The same consumer could be using multiple forms of these devices. What we deliver to the end user, is it the same static state that we have known in the past, or is it dynamic even for a single user that's using multiple devices for doing his or her job? And that's something which leads to my final point here is that the enterprise ecosystem is fast evolving. On one side, we have the evolution of the enterprise infrastructure ecosystem, the enterprise application ecosystem. The second is around the theme of how data is changing shape, how data is really becoming more and more pervasive. It's across the board. It is not contained anymore. It is boundaryless. And as you look at this picture, one thing that becomes very clear is what was static in the past is dynamic in the future and also fragmented. Your infrastructure is fragmented. Your application landscape is fragmented. Your data is fragmented. Your end user computing framework is fragmented. And I think the key challenges that we will all face going forward is how do we bring seamlessness to this fragmented IT ecosystem. And that is something I would place as a very important aspect that we as engineers need to figure out going forward. We need to look at the entire ecosystem in its entirety. We need to bring seamlessness to this entire ecosystem. We need to look at themes like security practices that goes across this fragmented ecosystem. And that's really where I believe a lot of energy needs to be spent going forward. And when we look at seamlessness today, if you're looking for a current experience, it's not that great. So I will leave this team with this thought, and maybe with the time that we have, we should probably go into the panel discussion.
Great. We have time for questions. So please come to the mics. I'll just go left to right or right to left as we see people coming in. Please try to keep your question brief. And if you want to target it to one of the persons, panelists, please do so. Otherwise, say that you want any of them to address.
Carl Reed, La Trobe University in Melbourne. A friend of mine in a European country I can't name was confronted with a very large national project where the government said, we want the result of the project to survive for 50 years. How are we going to deal with that?
I guess both enterprise people as well as Jeannette can take in that. Somebody wants to plan for 50 years.
This is actually very, very good question, and I think it's actually an open research question. Recently, I was attending a workshop that, in my capacity as co-chair of the ISAT advisory committee to DARPA, the workshop was called Ever Cloud. And the point was, how are we going to forever store and access all the data and all the code that interprets that data? And you know, the easy example is people store their pictures and so on, and their memories for life, and you'd like to be able to, for eternity, have generations of families look at those pictures. We don't actually know how to do that. And even harder are pieces of code that have to interpret any data. Of course, this has been a hard problem for a long time, but because of the massive amount of data and because of the storage being remote in this cloud that's a mystery to everyone, I think it's a more pressing problem. So I think this is a research question.
I can take a different crack at it, Jeannette. First of all, I think it's a question of setting expectations. So since this example is from Europe, I went to this cathedral once in Prague called the St. Vitus Cathedral. And it's a unique example of civil engineering which shows about 8 generations of patches, if you will, to the base code. It started in about 1100 AD, and the last patches were put in about 10 years ago. You can actually see the evolution of the cathedral from what it was in 1100 to 1300 to 1500. They're all different architectural styles. It was pre-Gothic in its earliest incarnation, and it was Baroque. It was now modernistic in the latest incarnation. So at least one branch of engineering, civil engineering, seems to have an example of systems which live for 800 or more years, 900 years. In software, I think we are reasonably good at building applications and systems whose end use case can survive many years. I personally have been part of a European project in the financial services industry where the original financial infrastructure was built in COBOL in the 1980s. And today, the core system still survives, but it has been evolved into a 21st century, more modern system, but still supporting the financial infrastructure of the European Union. So we do know how to build systems which can survive now, approximately 30 years. But I think it's a question of setting expectations to this individual that the system that we deliver today may not survive in its exact technical implementation for 50 years or more. The function may survive. It's quite debatable whether the business function itself would be unchanged in 50 years. But we think that we can evolve both business function and technical implementation, at least for that length of time. Maybe, but not for 900 years. So set expectations properly is what I would say.
Vishnu, you want to add anything?
No, I think an outlook of 50 years is probably wrong in this era. I would say that an outlook beyond 10 years at this point of time is very fictitious. And more so because of the onslaught of some of the technology trends that we have seen in the last few years, would probably take another 5 years to stabilize and to again give way for the next trend of technology disruption that might just come in our way in the next 10 to 15 years. So I would say that the theme probably should be in setting up projects and systems that are evolutionary in its approach, that allows it to evolve as these trends hit the market, as this trend hits research, as this trend hits engineering paradigms. There's still a lot of things to be done, but I think designing a system which is evolutionary in its construct is going to be the key thing in outlook of something like that.
Sounds good. In the middle, please. Sir. Yeah.
My name is Hari, and my question is like, both products and services, Microsoft, TCS, and Infosys, all of you have addressed from your client's perspective. What is going to be the demand or the changes that are going to come? What software engineers have to do to satisfy the demands from the clients? I would like to hear from you how the life of a software engineer is going to change with the new models, processes, and analytics that we are bringing into the arena. Does work-life balance will be more balanced? Does the higher productivity that we are bringing into the system is going to lead to better innovations because of there's more time probably available for the engineers? And is the life of the software engineer going to be more play than work?
Thank you. Good question. How does the life of the software engineer change? I guess different types of.
I can take the first shot at this. I think I would say that the life of a software engineer is going to be very exciting to start with. One is, I think, that the fundamental paradigm that is changing for a software engineer is, I mean, with this construct that we have just pictured and we talked about, is that the tools, the techniques, the themes, the compute, the infrastructure that you need to do your job is more readily and pervasively available. And that's number one in terms of what you can think of doing, because in traditional sense, if you look at if you wanted to do some interesting work and try out new things, the amount of time that you had to spend in procuring the tools, the infrastructure, and everything else you needed was way longer than we see today. But that's one thing that really changes. The second thing is that automation will provide a significant amount of respite in terms of the amount of things that you can do underneath that you don't have to worry about anymore. So there's a significant amount of time available for innovation, for doing new things, and so on and so forth. But one thing I would say that is important for the software engineer's mindset to understand is this changing ecosystem itself. I think as Jeannette was talking about earlier, for example, security takes a very different paradigm. Today, your application could be residing in any part of the compute framework globally. Your data could be residing in any part of the compute and storage framework. Your data could be delivered on devices of any kind, of any form, and used by anybody that you probably can barely track. So when you look at that ecosystem and the evolution of that, how does your application maintain the integrity of the process? How does it maintain the integrity of data? How does it maintain the integrity of security, and so on and so forth? These are the themes that needs to be understood, applied, and developed as we go forward. And that is something which will be important for the software engineer to start changing from a perspective.
So if I may just add, with all this computing everywhere, will a software engineer be able to program while being on a beach with a little drink with the umbrella sitting there?
Why not?
Yeah, I actually wanted to add something. First of all, I do imagine a day where the tools and environments for software engineers will make it so that they're much more productive. They are programming, if you will, at higher levels of abstraction. All the dreams that we have been working on in software engineering research for many years, I think we continue to make progress. If I just look back 10 years, at even at Microsoft, I see the difference that it's made in terms of the tools that are used, the verification engines underlying those tools, the specification languages and annotation languages that software developers use routinely at Microsoft. Now, looking ahead, I see something that we haven't discussed, which I think is especially relevant for the professors and academics in the audience in terms of training the next generation software engineers. And this has to do with the prevalence of data analytics, machine learning. I already hinted at systems that are going to have to work in the presence of uncertainty. What I'm really saying is that probability and statistics are going to be as important a mathematical foundation in a software engineer's training as is discrete mathematics. And so I would, and I see this already at Microsoft, where machine learning is one of the most popular in-house training courses. And probably many of the software engineers, when they went to school, never even had the opportunity to take an undergraduate machine learning course. So I anticipate that there will be a future where, being able to reason about probability and distributions and that variables can range over and so on is going to be the norm. Maybe I'm exaggerating, but that's something that I think the academic community needs to be cognizant of, because we are seeing this already in-house.
Ananth, you want to take a quick take?
Yeah, I think a couple of things in a software engineer's life are unlikely to change. I think technical expertise of various kinds, the ability to focus and work long hours, cold pizza and warm Coke is not going to go away. But I think to add to what a software engineer in the future would need, I think some of the right-brained skills, creativity, consumability of the code that we write, imagining what the true end user of this application is going to want and need. Some of those non-engineering aspects, I think, as well, would become very important.
So exciting, but we still have to work hard. So I'll go to the third mic and then go work back. Yes, please, sir.
Yeah, thank you. My name is Aditya. I work for SAP. Thanks for a very interesting panel discussion. I had a particular low-level question for Jeannette Wing. It was helpful to hear about all the secrets from Microsoft internals from research. So we should get more of the Microsoft people out in the open so we find out. So in specific about the SIMDiff tool, which was interesting, language independent, relative correctness checker. I was wondering, is this applied or rolled out for component level, module level, or a library to do a diff of like individual pieces of a program, or do you do it for like a whole big application? And in particular, SIMDiff, is it used for the large scale software that Microsoft releases, like, for example, SQL Server or some of the Office products? So I just wanted to understand the scope and applicability of this tool.
Yeah, that's a really good question.
Thanks.
Do I have any of my SIMDiff Microsoft people in the audience who can help me answer that question?
So
okay,
she wants help from the mic.
How about you talk to me after the session, and I will point you to the papers.
So we'll take 2 more questions. So this
Sandeep
you take offline after
available.
this. We'll take 2 more questions, then we'll break, but I'll request them to continue here for some time, but those who want to go for coffee. But you, sir, and then Bill, you. Yes, please.
Lutz Brechelt, Free University of Berlin. This goes to Ananth in particular. The range of considerations that you talked about were so massive that when I think about them as an educator, they make me really frightened indeed. What do you think, how many different disciplines, subjects, degrees should we have ideally in order to train the people who can do this, and what would those degrees be?
Right. How do you pack it in 4 years? How many degrees does someone need before you become a software engineer?
No, it's a great question, and we grapple with it as well because we hire lots of people every year. We run a large-size university inside our company, as does Infosys and many others. And we try to make this lifelong learning a reality. It's clear that a 4-year or a 5-year degree would not be enough for any individual to absorb all these capabilities. But I think educational institutions should focus on the foundation. Software engineering, as it is taught in universities, should probably become relatively more modularized so that people maybe who are majoring in humanities or majoring in economics or biology or something can also understand the basics, because as I said, developers will be in all kinds of disciplines in the future. Software engineers will certainly learn a lot of software engineering, but a little bit of many of the areas that I talked about in their academic courses, and the rest will have to be learned in practice. I don't see how somebody can, as you rightly said, learn all of this in a finite amount of time towards a degree. Maybe some modules will have to be introduced which are foundations for some of these, but the rest will be learned in practice as your job and role evolves in your careers.
You want to take a quick crack at it, or would you pass?
I completely agree that for whether you're studying software engineering or computer science, the most important skills to learn as an undergraduate are the fundamentals. If you're really strong in the fundamentals, then I think you can learn anything as the world changes, as technology advances.
Okay, Bill, last question. After that, we'll break, but I'll request the panelists to be here for another 15 minutes so you can come and ask, but let's, Bill.
So healthcare.gov probably was 500 million lines of code, but most of it was already built, right? It was already in insurance companies and Medicaid systems in the States and IRS and all these other places. And the problem was having to, as the SEI started work on a decade ago, we're now in the era of systems and trying to clap that together. But we keep taking a lot of the responsibility on ourselves for the problems rather than put it back on the enterprise. And so you'll see enterprises that have 50 different ways to do the same thing, and they're perfectly happy with that, which makes it a nightmare for us to try to integrate all those requirements and come up with something sensible that will actually work in decent time. How do companies like Infosys and Microsoft and TCS push some of the responsibility for simplifying what they want back on their shoulders and remove the log from their own eye before they punch us in the eye?
Bill, you're forgetting that generates business as well.
Well, yeah.
Please, you may respond.
No, Bill, I think it's clear that I haven't yet met an enterprise CEO or a CIO or CTO who says they love complexity. Bring it on, we need more. Everybody says we need to simplify, we need to bring things down to a bare minimum to run our business. And that's the intent. In practice, you're right. The amount and variety of use cases that businesses are asked to execute is multiplying the hockey stick that I talked about. So I don't think there is an easy fix. What in practical reality most of us end up doing is to limit scope at least for the first version or the first release or whatever might be the milestone, and get that out of the way and then start evolving the systems like even Vishnu talked about and the earlier question was. There is no way in which you can imagine all the different use cases for a reasonably complex business function. I mean, healthcare is not a reasonably complex, it's a very complex healthcare business domain. So I don't think we can limit complexity from the end use side. You can try to control it at a certain level and then evolve. There's no other practical solution.
So let us thank the speakers. As you'll see, 3 of them. Thank you. As you see, no coordination, and yet you see some common themes of speed and this thing coming, and yet very different perspectives. So I think I personally feel that much more enlightened after this talk. So I would like to give them a little gift, and I'm requesting them to stay for another 10, 15 minutes here for those of you who want to interact with them. Can I please?
It's probably a huge thing that.
You have an international flight to carry it on. I please have, we can get it domestic.
Oh, maybe we share it.
Thanks, man. Thank you.
Thank you. Wow, thank you. Wow.
Yeah.
Continue to stand up.
Thank you.
Oh, this isn't so bad.
Yeah.
Oh, really?
Thank you very much. Those of you who would like to interact, please come.
Thank you.
So please come up. They're here. You can come up here and talk to them. Please. Thank you.